Okay, so let's get started. So thanks everyone for coming tonight to Space Cafe Tokyo. So tonight we're very happy to have Dr. Kohei Ichikawa give a talk. So Kohei is an associate professor at Waseda University. Is the father of two children, one boy and one girl. He obtained his PhD from Kyoto University in 2015. And then after that, his research took him to several cities, including Tokyo, New York, Sendai, Garking, and back to Tokyo again. So today, Kohei is going to tell us about how astronomers observe supermassive black holes. So Kohei, please.
Thank you, Ken, for introducing me, and thank you for having me here at the Shimokitazawa. Actually, this is my first time to come to Shimokitazawa, so I'm happy to come here. Yeah, so and also my first time to hop on to the Oda-Q line. And then Oda-Q line, in Oda-Q line, a lot of people welcome me in the train. I was so surprised at that. Okay, today I would like to introduce about how actually I'm a professional astronomer and I'm doing observations, and then how the observational astronomers are actually observing supermassive black holes. That is a key message of my talk. And then before going to that, I would like to briefly introduce about myself. And then you have already noticed that my name is Kohei Ichikawa. And then if we write down my name Kohei, in Japanese we often write Kohei. Okay. And then I'm a researcher and I'm often going to the many countries, including USA. And every time when I go to USA, of course, I'm a tourist, for business, and I'm going to hotels. And then reception, they say, your name is Kohei Ichikawa, or Kohei Ichikawa, or something like that. And so they are not able to pronounce my name correctly. But I guess all of you are now living in Japan, so you know how to pronounce my name. My name is Kohei, okay? So that is one key important message from me. But don't worry, you already noticed that this Hei, actually the same of this Shohei Ohtani-san, it's a most famous MLB player, and now today it's now in a kind of big scandal or something. But actually, so that you already know, you live in Japan, you've seen this guy almost every day at the NHK or every news, so that you now know how to pronounce my name. Hei is actually the H-E-I, Hei, okay? So, as Ken already introduced, I was born in Osaka and then grew up there, and then went to Kyoto, Tokyo, and then also I spent some years in New York, and then moved to Germany, and then back to Japan Sendai, and now I'm finally back to Tokyo. Actually, I would like to briefly introduce about my name again, that, I was born in Osaka 35 years ago, and I was born as a second son among three brothers. I was the second son, so meaning there is one elder brother. He was actually already 10 years old at that time. And then his name was Yohei, and my name was Kohei, so that was already fixed by my parents. But my parents asked my elder brother Yohei that you can choose a kanji for my name Kohei. And then my brother took almost 3 days, and he chose my kanji name. So that he's a kind of godfather who gave my kanji name. So I'm really proud of that. And then probably most of you already forgot my name, but this is my kanji name, okay? And I explicitly write down from top to bottom that this is one of the reasons why I love my kanji name. And then I asked that one day in my elder brother that why did you choose this Kohei? This means happiness and peaceful. It's a nice name. Why did you choose that? Actually, he said to me, you can put a line at the center, and then you would notice something. And then you can see a very beautiful symmetric structure. This is why I chose this Kohei. That you can ignore as a part of this river, but that is the reason why he chose my name. Okay. So thanks to that, I was quite very sensitive about the symmetry stuff, and so I was became loving science and mathematics, and finally became an astronomer, and this is my profession now. Okay. And actually, it's already 8:10 p.m. 8:10 p.m. for me. It's kind of the time for going to bed with my kids. And then so this is a kind of like my first time to go out after 8 p.m. Like that is almost my first time like after COVID. And then, so I'm feeling a little bit scary, but I'm happy to see. And thanks for giving a great opportunity, Ken, and organizer here, and also the owner of this pub, and also my wife at school, to giving me a recommendation to give a talk tonight. Okay, so probably most of you have never met professional astronomers, and then so sometimes when you go to like a haircut, and then if you are professional astronomers, you ask that what's your job, and I'm saying I'm astronomer, and then the first reaction is always say like, wow, great, it's cool job, and then wow, I've never met astronomers before, and the next question is always something like this. Do you see sky every night, or like were you aiming to become astronaut? So that is a kind of very, very typical questions I received already 100 times in my life. But actually, if you are a professional astronomer, such kind of question never came out, because currently most of the observations are doing remotely, and then we don't have to wake up every night. Okay, so we can do the science on the daytime, okay? And then we sleep with my kids from 9 p.m., okay? This is why we can do the professional astronomer here. But that's a quite natural outcome, because, most of people have never met professional astronomers, and then so most of people never thought about astronomy. So it's a quite natural things. And I just, I'm an astronomer, so I just wanted to check why the people never met astronomers. This is because one of the reasons, population density of the astronomer is quite small. For example, like let's check how many astronomers are in the world. Let's pick up one example. We are living in Japan, so let's check how many astronomers in Japan. So if you are professional astronomers, you should always register Astronomical Society of Japan. And let's check the number of participants, number of registers, and it's roughly 3,000. Okay? And then we already know that Japan's population is roughly 1 billion. Okay? So sorry, 100 million. Okay? So divided by that number, so the density of astronomer is like 2 times 10 to the minus 5. Sorry for using power of that. But roughly, in other words, it's a 1 in 40,000 people. Okay. On the other hand, okay, so if you meet 40,000 people, you can find astronomers, but actually it's not, because your lifetime is limited. Okay. So your lifetime, if you live long, but it's just 100 years. Okay. And you already know how long is 1 year in by day. It's just 365 days. Okay, so your lifetime is just 40,000 days. Okay, so that if you meet one person per day, and if you ask their professions, and in your whole lifetime you will meet only one astronomer. Okay, that is how rare astronomers are. Okay, so that now you are getting such a rare opportunity now that you already meet at least one professional astronomer in front of you, and so hope this will be a good opportunity or a good experience to most of you. Okay, so I'm an observational astronomer, and I would like to introduce one key concept. Is that how to observe black holes. And the second important point is there are 2 types of black holes: the small black holes and big black holes. It's called supermassive black holes, or SMBHs. And then I'm observing these SMBHs. So the hope, if we remember that what are the supermassive black holes or SMBHs, it's a quite big success for me. Okay. And by the way, if you have any questions, please interrupt me anytime. Okay. So then let's start. How to observe black holes. Okay. So actually, we already know that there are a lot of black holes, but you also know that in sci-fi that black hole is an invisible object. So you might think that black hole is almost impossible to observe. It's partially correct, but partially not true. Of course, that's true that black hole itself, themselves, are actually very difficult to observe. But we are living in our universe, and then we are living on the Earth, and we already know that there are a lot of matters or gas in our universe. So if there is a black holes, of course, surrounding a black hole, sometimes there are a lot of gas. Okay, and then if the gas means to black holes, you can imagine like a kind of put the top on the thing, and then you can see the water. Okay, and the water is finally going to the hole of the thing, something like that. That hole is a black hole. Okay, so the black hole is there, and if there is a lot of gas is falling to the around the black holes, such gas is falling to the black hole because of the very big deep potential of black hole, and then gas is falling to the black holes. And then the important thing here is you did this kind of stuff in junior high in physics class. When something moving from higher place to lower place, because of the conservation of the energy, you have to change that energy to something. So in case of falling from top higher place, lower places, they are changing potential energy to the kinetic energy, so the moving faster. Okay, and then a lot of gas is falling to the center, and then sometimes gas is attacking each other, or like it's called frictions. Okay, friction is like this. Okay, it's called frictions. And then if gas starts a friction, that produces something. So does anybody say heat? Heat. Okay, great. Yes. So the friction produces heat. So that finally the potential energy convert to the heat. And if it's converted to heat, thermal energy in physics term will be converted to the light. Okay, so we are also very bright because we are roughly room temperature. In a scientific term, it's around 300 Kelvin. We are a black body of 300 Kelvin, and then we are very, very bright when you have an eye of the mid-infrared, and then all of you will be really, really bright. Okay. So, in case of black holes, because of the very deep potential, so that can easily efficiently convert that energy to the thermal energy. And that thermal energy is going to really, really high. How high? It's going to around, in case of typical black holes, like a typical stellar mass black hole has, we astronomers using a mass of the sun. It's called the solar mass. And the mass of the sun is roughly 10 times the mass of the sun for typical black hole. It converts temperature reaches around 10 million Kelvin, or 10 to the 7 Kelvin. So it's really, really hot. Okay, so very hot. So if the energy temperature is high, it emits a really high energy photons. In case of temperature of 10 to 7 Kelvin, it's an X-ray. Okay, it's a Röntgen light. So this means if you want to find black holes, you have to observe the sky in an X-ray eye. Okay, so if you have an X-ray eye, you are able to find black hole candidates. Then let's check. This is a part of the sky. If we observe the sky, it's roughly only 0.2% of the sky, but the darker places, there are no photons of X-ray, and you see many white points. All these white points are the X-ray bright points, meaning actually there are roughly in this field there are 20,000 X-ray bright points, meaning we have 20,000 black holes in the sky. Okay, so that if we have X-ray's eye, we are able to find black holes. Okay, and we already know that thanks to the X-ray astronomy, and then of course that if we want to X-ray astronomy, you have to launch satellite and you have to observe them from the satellite. Okay, so otherwise we will die because X-ray kills you. Okay, so the atmosphere protects us from the cosmic ray or X-rays. This is why that we are able to survive on this beautiful Earth. Okay, but if you go to the space, we are able to observe black holes by using X-rays. And then among those black holes, I would like to introduce two types of black holes. And then my favorite one is a big one, but let me start from the small one. Okay, the small one. Actually, we already studied that in order to observe black holes, we need a gas, or we need matters, or anything is fine, falling to the black holes. So if we have only black hole alone, we are not able to observe. But if there is a partner, and if the partner has a gas, for example, the sun or something, and it's close enough, black holes can get rid of the surface of their partner's gas. Okay, so that is a situation here. So it's called the black hole binary. We use the term binary, meaning black hole has a partner, and the black hole can grab the gas from the partner. Okay, and then that produces a so-called falling gas. It's called accretion disk in physical term, and then that becomes bright. Actually, we already know that roughly 20 or 30 such kind of black holes, but it's actually only kind of tip of icebergs. Okay, so that we can get that such kind of black holes can be made after the a supernova explosion, which is a final phase of the big stars, like at least 10 times bigger than the sun. And then that would produce a black holes. We already know that. So that and we already know the history of the Milky Way, so that we already know how many such big stars were already dead in our Milky Way. And then we count that it's roughly 10 to the 8 black holes. So so in our Milky Way, there are 10 to the 8 black holes. But we already know only 20 or 30 black hole binaries. Okay, it's observable in X-rays. So the key word is this black hole is called the stellar mass black holes. It's like a solar mass like black holes, and then their body weight or mass is just 10 times the mass of the sun. In technical term, we use 10 solar masses, and the luminosity is how bright they are. You don't have to remember the number, but it's 10 to 37 to 39 every parsec. We astronomers love to convert that is divided by the brightness of the sun. So actually this is roughly 1,000 to the 10,000 times brighter than our suns. Okay, so it's really bright. Black hole is really tiny, but they're bright roughly 10,000 times of the brightness of the sun. So actually, most of them has been found through the black hole binaries, but there is only one path now that we are able to observe, even if the partner is not, say, typical, if they don't have partners. One is gravitational waves. All of you should know Einstein, okay? And Einstein's one important work is general relativity. And general relativity expect that if there is very big stuff, and if these very heavy stuff is rotating each other, it produces a curvature of the space-time. In other words, it will be a production of the gravitational waves. For example, even if we are like you have anything with a mic and you are moving like this, it will produce a gravitational wave. but level of gravitational wave is very, very, very tiny. So this is what we are not able to see that. Okay, but in case of stellar mass black holes, it's 10 times the mass of the sun. It's big enough, so that it produces gigantic gravitational waves. Roughly 20 years ago, when I was undergrad, I was told from my friends that we were not able to observe such gravitational waves, so that you should never go to a gravitational wave in physics or like a laboratory of that. So I avoided that. But actually, now we are able to observe them, and then this is the first detection of the gravitational wave thanks to LIGO in US in 2015. LIGO is there is a too long interferometer. I'm skipping the details, but LIGO can detect such gravitational waves by using a very long interferometer. Yeah. Now similar gravitational wave detectors built in Europe. It's called Virgo or Virgo, and then now we are also Japan also has one interferometer. It's called Kagura. So now it's a LVK collaboration, and we are doing collaborative gravitational wave detections of that. And then this can find a lot of binary black holes, and then the mass is around 10 to the 100 times the mass of the sun, relatively larger than the black hole binaries. So this is a list of the black hole binary black holes LIGO has discovered. It's already over 50 sources, way higher number than black hole binaries observed by X-rays. So now LIGO or gravitational wave is the most efficient way to find stellar mass black holes. That is a new pathway to find black holes, which has been discovered, which has been made in the last 10 years. Okay. Can I move to the supermass black holes? Any questions? Okay, looks like everybody already mastered how to observe the stellar mass black holes, and then we would like to move to the supermass black holes. So supermass black holes, big black hole. Actually, we already know that these big black holes are located in the center of galaxies. For example, I already told you to find black holes, we should observe in X-ray. Left figure is one galaxy observed in our visible bands. We often say optical bands. You can see a beautiful galaxy at the center. And let's check the same galaxy in X-ray eye. And the result is like this. Okay? So we can see only one point and located at the center. And then looks like, oh, there's a black hole at the center of the galaxy. And probably it has this kind of accretion disk, and this is why we are seeing very bright sources. And actually, from the spatial resolution, I'm not sure how to say in usual term, how to thanks to the big good eye by X-ray Chandler, we are getting this size should be really very small in terms of astronomy. It's smaller than the distance between Earth and Jupiter. Looks gigantic, but actually very, very small. Because we already know that it's very brighter than a host galaxy, and it emits only this tiny area. Okay, so this is called looks point source. Looks like a nucleus, so that we call them active galactic nucleus, or in plural we say active galactic nuclei, or AGN. In Japanese, if you are familiar with Japanese, please check 活動銀河学. That is a technical term to find such active black holes. And let's check AGN first. How bright they are. Actually, we found many AGN through the X-ray and optical observations, and this is an optical image. As you can see, there are a lot of galaxies. And if you look at the same area with X-ray, not always, but we see some of the points. For example, these 3 points, it's this one. Okay, so the sum of galaxies are bright in X-ray, meaning galaxies host AGN. Okay, in other words, they have black holes. And then we know the distance, and then we know how bright they are, so we can calculate the luminosity, how bright they are, brightness. You don't have to remember the number, but important part is they are really bright. How bright? Compared to the brightness of the sun, roughly we need 10 to the 9 to the 10 to the 13 times the luminosity of the sun. So they are really bright. So it's surprisingly bright, okay? So it's already exceeding stellar mass black hole's brightness, so that we were so surprised. How can such luminous object exist? So that we wanted to check again that the next step is checking how heavy they are. In other words, the mass. So we can find a lot of gas around black holes, and then we can spatial resolve and checking the rotation of the gas. Then you are able to do a very basic science, Kepler motion. Okay, Kepler motion means if you know the how rapidly they rotating, you can guess the mass at the center. That is how the Earth and the Sun relationship. Okay, so that we check how rapidly gas is moving there, and we check that, and the expected mass of the center object should be 3 billion times the mass of the sun. Okay, so anyway, huge. Okay, so that we introduced stellar mass is 10 times the mass of the sun. It's now 3 billion. Okay, so 8 orders of magnitude difference. Okay, so gigantic. Universe is huge. Okay, so we got such big black holes, and actually we now know that a lot of supermassive black holes, and then that mass is the lower limit is actually put at 1 million times the mass of the sun to the 10 billion times the mass of the sun. So we still have 4 orders of magnitude difference from the black holes discovered LIGO or X-ray binary, and then the one we found in the center of galaxies. It's surprising, okay? And then some of you might be familiar this kind of a donut shape image, which has been reported already 5 years ago, I guess. It's in 2019. So this is a M87. Actually, this is the same galaxy, okay? So this is M87. This is the center of galaxies. They found such ring structure, and the black hole mass is proportional to the size of the ring. So by checking the size of the ring, actually they also got exactly the same value. So it also provided robustness of our mass estimation method. Okay. And then you might wonder, we are living in our Milky Way. We want to know, do we have supermassive black hole in our Milky Way? And actually, yes, we also have black holes at the center of Milky Way. So this is this bright point is the stars, and as a function of time, and then we observe them, and the star is rotating, orbiting, and has an orbit, and the central point. But actually, this central point in this star is artificial, so that nothing there. Okay, so that they are quite bright, quite dark. Okay, pitch black, but stars are rotating around such black hole area, and based on that we checked black hole mass, and it's 4 million times the mass of the sun. So we also have our Milky Way also has such big black holes. It's surprising, and that results recognized a Nobel Prize in Physics in 2020, and then given to Andrea Goetz at UCLA, and also Reinhard Getzel in MBA, Germany. And actually, related to that, in a different galaxy, actually, I would like to mention one astronomer in Japan also contributed a lot. His name is Miyoshi-san. He is in NOJ, and then he also did a pioneering work related to such discovery of the black holes roughly 30 years ago. Yeah, that was clearly mentioned in one of the reasons of the Nobel Prize in Physics. Yeah. So okay, let me summarize the mystery in our universe. So the question is, how can universe make such big black holes? So we already know that black hole is supermassive black hole is huge, at least 1 million times the mass of the sun. And we still do not know how such a big black hole was made. So we need some fundamental mechanism. Why is, new path that, making such big black holes? And the other way is, we already know that how to make a small black holes. So that by putting us there, that will increase, they will grow now. So that by doing that, we might be able to make such supermassive black holes. But it takes time, okay? But we already studied very two important things. If gas is falling to the black holes, that always converts the energy to the light. So it becomes light, bright. So the gas is falling to black hole means it always becomes bright. So that we are able to observe them. And even if the other ways, two black holes colliding each other, that will twice the mass of the black hole. Yeah, of course, number is decreased. But, in such case, again, it does not emit light, but it emits gravitational waves, so that we are able to observe again. Okay, so that is the two key pathways to check, growing path of the black holes. I'm doing both of stuff, but I'm introducing only the, number one part only today because of the lack of the time. But you have any questions I can introduce the second part as well. Okay, so let me pass through the final part, and then from here, the talk will be quite professional level, so that you can just drink beers and then listen my talk like a jazz. Okay, so it's really difficult part, so that if you find many technical words, just forgive me. Okay, so let's recap about AGN. Okay, so it's a gas accreting event to the supermassive black holes. And then we already know that the center black hole has a mass of 1 million to the 10 billion times the mass of the sun. And then I would introduce, it's a good object because it's a growing phase of black holes. Black hole is eating and growing their mass. And I didn't mention at all, but actually one beauty point of AGN is they are actually bright in any multi-wavelength light. A very difficult technical term. It's bright not only in X-ray, but actually they are bright in UV, they are bright in optical, actually they are also bright in infrared, and actually also bright in radio. So they in any wavelengths, we have to observe HN. So that's a beauty point of HN. Okay, and then in order to know how rapidly they are growing, it's a very difficult term, but total mass should be like a number of eating per time, okay, and the times total number of time. So that we the observe what we are observing just a one shot. It's a camera, so we can get okay. So the one guy is eating 100 grams of the steak per night, but we want to know how much number of steaks they actually eating. Okay, so this T is also unknown actually. Yeah. So we want to know those two values. Okay. So I would like to introduce how we are able to see AGN in radio. So this is a AGN in radio. It's a beautiful one. At the center, there is a black holes. Okay. And sometimes black hole produce a very gigantic jet, and then that is hitting to the surrounding gas, and that produces a so-called jet lobe. The beautiful one, okay, and at the center, there is a accretion disk and black holes again, and this is a schematic image, okay. So that today's, such kind of AGN is ignite once the gas falling to the center. That is what I told you several times already. But one big question is that we still have never observed the ending point of this AGN, okay. So we still do not know how long AGN can last. Okay, so we still do not know the lifetime of AGN at all. And then if there is a starting point, it always should have an ending point, okay? So otherwise it will be infinity, okay? So, but we are not able to find such final phase of AGN yet, because we already know that AGN lifetime is very long, longer than our human time scale. One human time scale is just 100 years. But we already know AGN should be lasting over 10 to the 5 years, so that it's very long. So it's very hard to see such final phase. But we found such a source, luckily, and we now know how to find those Asian systematically. So I would like to do such one serendipitous discovery of that. So this is a one Asian, that name is UP187, and as you can see, UP187 has this two bimodal beautiful jet. Then we already studied that if there is a jet, there is an Asian. That is what we saw in the previous slide. But actually, UP187, the key component is missing. That has in the right panel. That is central core. Okay, so there are no central core, but the lobe is really bright. So that definitely it has Asian. But somehow, core that should associate to the black hole accretion disk is missing. So this means current Asian activity might be really silent. So if you are a professional astronomer, you might be wondering it's an obscuration effect, but it's observed in ALMA, so it has a really strong upper bound. So definitely it's a non-detection. Anyway, so let's check this UP187 in a different wavelengths, and then we might see much more better information. One is observing them in optical band. One beauty point of the optical band is we are able to see a plasma. Plasma is ionized gas. If there is high energy photons hitting to the gas, it becomes plasma. Okay, so the gas is heated up and then it's ionized. Okay, it becomes plasma. In case of AGN, they are gigantic energetic event, so that it can ionize surrounding area up to 1 kiloparsec. It's 3,000 light years. Okay, 3,000 light years. This is a green color one is ionized plasma observed in oxygen in optical band. So that is a typical ionized gas regions observed in AGN. And then this UP187 is also bright in this is a spectra, and we see a very strong oxygens. And if we check that how brightness they are, we get they are bright like roughly 4 trillion times luminosity of the sun. So it's really bright. Okay. But again, if we want to check the central part, X-ray is always the best. So that we asked the NASA NuSTAR X-ray satellite to observe them, and then NASA gave us the time, and then we observe them. It's a gorgeous telescope, and then we get the result. The result is like this, as you can see, nothing. Okay, so we use a gorgeous NASA time, whose taxpayer is USA citizens, and then thanks to that, by using the tax of USA citizens, we get this kind of non-detection image of that. And actually, this gives a really strong upper bounds up to the 10^42. The number is, you don't have to worry about the number, but the important part is, central region. It should be 5,000 times fainter than the value expected from the surrounding gas area. Okay, so this agent experienced a rapid luminosity decline. So let's summarize, what's happening in UP187. So the typical agent has both of bright nucleus and gigantic ionized regions. But actually for UP187, there is a gigantic ionized region, but the central engine seems quiet. Dark in radio, dark in X-ray, I didn't mention, but dark in infrared. So this means the one possible reasonable way to understand is that for the extended area, it has a length of 3,000 light years, meaning we already studied the speed of light is finite. So if the light is traveling to this direction, it takes at least 1,000 years to reach to the edge of the cone. So at the edge, that bright area still does not know that central engine is already quenched. So that luckily we are living in like this way, so that we are able to see such kind of ionized gas region as a time machine, using as a function time. So based on that, within 1,000 years, this R27 experienced a rapid shutdown of the Asian activity, fainter than nearly 10 to the 4 times within 1,000 years. So we call them, it's a dying AGN, so the final phase of the AGN. Central engine is dead, but still we see a remnant in larger scale. Okay, so wrap up, so that we found such dying AGN, and then actually we have found a lot more sources. Actually, now later studies, we already have like 10 such candidates, and then based on that kind of number of fractions, actually we are able to estimate the lifetime of AGN. It's very hard to understand, but by checking the ratio of the dying AGN over the total number of AGN, it's a ratio of the lifetime, and then but the dying AGN is able to observable only 1,000 years. Okay, so if we find dying AGN 1 out of 10,000, so the lifetime of the typical AGN should be 10 to the 7 years. It's a little bit hard, but that is how we are doing science. And then so the this dying AGN gives a lifetime of AGN. That is one of my main studies. Okay, it's almost finished. And so I introduced supermassive black holes, and then such supermassive black hole can be observable as AGN, and then AGN can produce a gigantic structure over 1,000 light years. By using that, we are able to use them as a time machine or clock of that, which is way longer than our one human lifetime. So that is a one beauty point to do astronomy, and if we want to know the much past of that, astronomy is the best way. Okay, so that's it. Thank you very much.
Thank you, Kohei, for a very interesting talk. So we have some time for question and answer, so please raise your hand and I'll call on you.
Thank you. Thank you for that interesting talk. And I was wondering, in the context of the mass of the black hole, are there no intermediate mass black holes?
Yes, so there are several reports about intermediate mass black holes, like a 10⁵ solar mass of that. But below the 10⁵ solar mass, there are no like a robust results actually, between 100 to the 10,000. That is a kind of missing zone.
Is it because of observational method that we are using, or is there actually the gap between them?
Yes, actually, we still do not know what is the origin. But the one reason is, actually, the black hole mass. If the black hole mass is, gets smaller, the brightness from the black hole also decreased. And then 10 to the 5 solar mass black hole is a kind of borderline between the host galaxy's brightness and the central black hole's brightness. It becomes almost comparable. So below the 10 to the 5 solar mass black hole, it's very difficult to detect the central emissions. So that is one of the observational bias that we can tell. Yeah.
Hi. So I'm just curious, theoretically, can a black hole ever be nullified, gone?
So you are talking about, decrease the mass of black hole?
Can it ever truly disappear?
Yes, theoretically, for example, Stephen Hawking has a suggestion that, based through the Hawking radiations, the black hole, some of the mass of the black hole can be decreased. But important part is, if we use such Hawking radiation, it's called Hawking radiation, it roughly takes 10 to the 50 years for one stellar mass black hole. Okay, so our universe age is way shorter than that. Okay, so considering that, generally black hole never disappear. Okay.
That's what I thought.
Yeah.
Question
Yeah. Yes, sort of leading on from that, in the observation you had where the way the jets suddenly stopped,
Yeah.
and so you're thinking that perhaps the engine died of the black hole. But then two things in my mind on that is are you able to observe black holes that aren't feeding? Because a black hole that's not feeding wouldn't have any jets. And then, with the idea of the Hawking radiation taking so long, is there some mechanism that you can think of that as to why it would suddenly stop producing the jets?
Yes, concerning about it's a really important question. How the eating stuff decreased for black holes. Actually, one of the reasons why black hole, actually AGN becomes faint is the decrease of the food in the surrounding area. Okay, but the actually important point is generally even if food is food supply is stopped, still black hole has their own accretion disk. So that the such disappearing time scale is generally roughly 10⁵ Okay, so my result is almost edge of the boundary condition of the theoretical accretion disk of that. So actually our result also give a feedback to the physics of accretion disk. This is also important part that I didn't mention. Yeah.
Okay, thank you.
Yeah. Yeah.
Yeah, so considering that black holes generally do not have an endpoint, they keep on existing. But when you speak about AGN that is, as you suggested, is dying, it keeps on existing, right?
Yeah. So the black hole itself exists, but they are not.
They're not
They are no food. Yeah.
Okay, I see. And is there a distinction to make there between supermassive black holes and smaller ones? Do we have a capacity of becoming a non-black hole in that sense?
So let me understand your question. Your question is how to distinguish such dying supermassive black hole and the small black hole. Is that
Yes.
what you're saying? Yes. First, I mentioned the brightness for this case. They said the brightness is roughly the 4 trillion times the luminosity of the sun. Okay, so if this is produced by a smaller black holes, actually there is a the space is limited, and then the maximum efficient way to eat is that black hole is here, and if food is falling all around the directions, that is the best way. Okay, and then so theoretically there is a maximum limit how we can eat the gas per time. So actually this is exceeding roughly 1 million times larger value than the expected limit of the small black holes. So we need larger black holes, and the larger black hole can get more food. So this is why one of the reasons why we need a supermassive black holes. Yeah.
Okay.
Yeah.
I finally a bit more basic question. You mentioned that the luminosity of the black hole was, I think, 10 to the power 10 of that of the sun.
Mm-hmm.
Is this in the X-ray spectrum?
It's a really good question. Actually, as I mentioned, that AGN is bright not only X-ray, but also bright in UV, optical, mid-infrared radio. Actually, the most of the emission comes from UV photons. Yes, and then X-ray is only the 10% of the total luminosity. So actually the AGN is most bright in the UV. Yeah, good question. Yes.
Finally, what's the sun? What is the fraction of the emission in the UV in the sun for comparison?
For the sun is bright. The most of the emission comes from the photosphere. Okay, and then we already know the photosphere has a temperature is around 6,000 Kelvin. 6,000 Kelvin has a peak around 0.5 micron. It's a green color like this. Green color like this. Okay, so the most of the sun's energy comes from optical. Yeah.
Yeah. So the
said that the ARC-187 was discovered by accident. So I'm a little bit curious how that accidentally discovery happened.
It's also a good question. Completely skipped that part. Actually, such discovery was first, ARP 187 is one of the ARP catalog, which has a lot of weird shaped galaxies made by, probably Mr. ARP, I guess. And then, and ARP 187 is also the remnant of the two big mergers. Okay, a merger means two galaxies colliding with each other, and finally it merges into the one galaxies. So the ARP 187 is also the galaxies who experienced a big merger event in the past. Okay, and then in such case, one important point is in a very very technical part, but actually there's some theories that if we experience the big mergers, they will become elliptical galaxies. Yeah. So in such case, we want to check how much of the gas is stored there. And this is why actually one of my collaborators, Junko Ueda-san at NOJ, observed this source by ALMA. Okay, and then through the observations, they found the reasonable result, but they also found that some bimodal jet structure as well. And then she asked me, "Hey Kohei, does ARP-187 has AGN or not? This is really important." That is the first part. That happened like the first year of my postdoc in 2015 in NOJ. Yeah, that is a starting point. And serendipitously,
she had a suspicion that something.
She thought that this should have AGN, but something is weird. Yeah. Because we didn't actually at first I didn't think this is AGN, because at first this is we had a much more coarse image. Now we get a follow-up observation. This was we get such sharper image, but at that time that is like slightly extended like this, and we were a little bit doubt. Yeah, but no detection in mid-infrared, no detection in radio, and no detection in X-ray, and I'm now confident that central engine is quenched, and then there is AGN in a large scale. Yeah.
One more just quickly. I think you mentioned that since then there have been several to 10 more have been discovered at that time.
For such kind of fading AGN, yes.
So is it that you have developed some techniques or something to
Yes.
efficiently?
Now you can also do the same science because you already know everything. So what we used is we try to find the AGN who are bright in a large scale, but faint in a small scale. That is how we selected. So that we first started from the AGN who are very bright in such plasma. And then we already have such kind of gigantic AGN selection or collections. It's called a catalog in our term. We have 100,000 such AGN. And then we check central engine. And then we found some candidates who were really faint in the center. That is how we did. It's simple, okay? Very simple. Starting large scale, bright, but central scale, small, faint. And we found such candidates. Yeah.
So the list is basically something like data mining.
It's a kind of data mining, data science, because we already have our sources. What we are doing just data science, yes.
Thank you.
Yeah.
Any other questions? Yeah.
Just one thing, if the AGN is defined by the accretion of gas, then can the dying AGN become active when there's another massive approaching nearby?
Yes. Yeah. Once new gas chunk is falling to the center, that will should be ignited. Because one of the reasons why I'm thinking so is that the expected lifetime from such a study is just only the 10 to the 6 to 10 to the 7 years. But actually this is not enough for us to describe the central mass of the black holes, so that we need episodes like flickering. But the flickering time scale is 10 to the 5 or 10 to 6 years. Okay, so flickering on off on off on off.
So it could be a dead, dying AGN could be revived.
Yeah, it's a kind of breaking time for them, and then we'll be back. Yeah.
So dying has one continent, one direction.
Look, sounds like one direction, but actually it's a kind of
It's more
getting a
silent-
break.
silence than-
Yes, just a silence, and then we'll be, or maybe in a sleeping time. Yeah, and then we'll be waking
Sleeping
up.
time,
Yeah,
that's fine.
wake up again, and then sleeping again. Yeah, that is our human lives. Yeah, but lifetime such
So
life cycle is
lifetime-
just 10 to 5 years. Okay. Yeah.
Thank you.
Maybe one more question, if anybody. Yeah.
What is about the black hole that we care as a community? I understand it's a bit of an anomaly, in the universe, it's heavy, it black, it sucks everything in. But why do we care? Does it unlock some secret mystery or some hidden law in nature that we don't understand? Or is it just an intellectual curiosity?
So let me check my understanding of your question. How does existence of such AGN related to us?
Yeah, why
affect
does it matter?
us?
Let's say we understood black hole now. So what is the difference in the life? Do we just things change, or do we have?
There is a one big consequence existence of black holes. It's it's a future of galaxies. Okay, so if there is AGN, as we can see, it's ionized, meaning all of the ingredients to produce stars will be almost impossible because it's so hot, so that they are not able to produce stars anymore. So if there is an agent at the center of galaxies, that killing the future stars, meaning the future planets around the stars. So that it also tells that we were in a really lucky situation that we succeeded avoiding such effect of the AGN, because we already know that the Milky Way also has black holes, and the black holes definitely had the AGN phase. Now it's dormant, but should be AGN phase roughly 10 to the 4 years ago or something. Yeah, so that is one important point to understand our future. If they started active, wake up, and then starting to project that to our directions, we will die. So we should be prepared for that. Okay.
Okay, thank you, Kohei, for a very nice talk again. So let's give Kohei one more round of applause. Okay, so I'm just going to end with a few advertisement slides. Okay. Thank you again for coming. We are at Space Cafe Tokyo. We have events here pretty much every month. And I'll post our social medias at the end. This bar is Good Heavens British Bar Tokyo. You can follow them on Facebook and Instagram. They have a lot of other events besides Space Cafe here, so please check them out. So a few of their events coming up that they want to be advertised. So this Saturday at 5:30 p.m. there's a Hafa and Friends meetup event. And then Sunday, April 7th, they have quiz night at 7:30 p.m. And every Sunday, starting from 1 p.m. onward, they're doing their Sunday roast here. I haven't tried it, but I hear it's very good.
By the end of this month.
Oh, okay, until the end of this month. Okay. You can follow them on social media to hear about their other upcoming events as well. Okay, so we have a partner event called Nerd Night. So this goes on in Kawasaki, and they are sort of a similar type of event, although not necessarily space themed, more general themed, and they have 2 to 3 speakers every time. And their next event is going to be on April 19th, which is a Friday, at the World Peace Theater, again in Kawasaki. So their speakers are going to be talking about volcanic exploration and badgers, apparently. So you can follow them. They have a website. They're also on Facebook and Meetup. Our next event will be actually the day before Thursday, April 18th. And it'll be right here at Good Heavens, and the speaker will be Professor Kip Cannon from the University of Tokyo. So if those of you who are familiar with Nerd Night, he actually gave a Nerd Night talk several months ago there. So he'll be giving a sort of an extended version of that here next month on April 18th. So please check us out. And then fine. So I have to warn you, our QR code link to sign in is broken today, so don't worry about it. We'll fix that next time. So ignore that. But please follow us on Facebook, Twitter, Meetup, and we also have a YouTube channel where Chase has been recording all our talks. So this talk will be uploaded hopefully within the next week or so. So you can see some of our previous talks as well. And so the Space Cafe Tokyo team, I'm Ken, Mayuko is at the door today, and Chase, our photographer. Tolino is not here today, but he's also one of our organizers. And yeah, you can follow them on social media as well. So yeah, that's the end of the event, and Kohei will be around for a little while, so please feel free to talk to him about his talk, anything you didn't understand, or other participants as well. Grab another drink, grab some food, and see you next month, hopefully. Thanks.